a little bit about the test, because I've been working on writing it, so let me tell you how I'm going to do it this time. So I'm going to revise something I said before. Last time I think I told you that I would give you either related groups or independent groups test. And I think that that's going to make each thing too expensive in terms of points because there aren't enough steps. So I'm actually going to have you do at least part of each kind of test. You'll do one at least in its entirety and then at least part of the other one, because I don't want any one thing to be so expensive in terms of points that if you make a mistake early on, it's this catastrophic mess that gives you a really bad grade. So it's better for me to give you more things to do so you have more chances to be right than fewer things to do, so if you screw up, then it really hurts. So you should, you should be prepared to do a full independent groups T test and a full related groups T test. With regard to the article that we talked about last time, you want to know things about that study, like, what was the independent variable? What kinds of things were they looking at in terms of dependent variables? Did they do between subjects comparisons or within subjects comparisons? What kind of t-test did they run? Were they independent samples or related samples? If I show you the table from the article, you should be able to tell which results were statistically significant. Right? You should be able to tell which group had the higher mean, for a particular dependent variable, something like that. So please make sure you know those kinds of things, where we're applying concepts. Were there tests, one-tailed tests or two-tailed tests, given their hypothesis, right? So the kinds of questions that show you can apply concepts from the course to that particular article. Okay, does that make sense? Do you feel like you can answer those questions based on our previous discussion? So I have to ask you first before I go on, what's going on with this class and why are half the people here again? Do you think it's just they're all like, oh, it's all on video, I don't need to go to class? Do you think that's what's going on? Or they don't like me? Should I feel hurt?
No.
I think everyone's bitter that school wasn't canceled.
Everyone's bitter that school wasn't canceled? Okay, well, I'm just checking. So you should also know just the problem set is, if you can do the problem set, how was it? Did you feel like you could get through it given the notes that we had? You could answer questions? Okay. So know that I'm going to ask you questions like on the problem set. I'm all about application, all about actually doing the math, although on the test it will be, I'll say things like, okay, so for this problem, calculate the relevant sample variance, and I'll give you the symbol to say, calculate this sample variance. Okay, calculate this estimated standard error. Okay, calculate this, right? I will tell you specifically what it is I want you to calculate. Please make sure that you show all of your work, the easy stuff. Okay, show all of your work, and that when you have short answers, that you try to make sure you answer the question I ask, not the question you wish I asked. And be specific. If you say, oh, she's asking me a question about this, don't brain dump everything you can think of about that topic into the answer. If you have, 2 sentences worth of space, be thoughtful about what 2 sentences you give me, because I don't want people writing down here and then writing down the side of the page and then flipping the paper over and writing across the back. Just answer the question. If you know the answer to the question, you should be able to do it in the space that I give you. So make sure that you thoughtfully answer the questions that I ask, and don't just try to generate as much information relevant to the question as possible, hoping that the right answer is in there somewhere. And I'm not going to data mine long answers for the right answer. So let's start with, talk about problem set 2. Can you tell me where you would like me to start?
Number
1A? 1A? Okay. 1A. Keep in mind, we probably will not have time to go through the whole thing today, so you want to be thoughtful. We won't be able to go through the whole thing. Yes, 1A.
Can we start at the back?
Yeah. Start at the back.
Like start with number 7 and work our way forward.
Number 6.
Okay, so you want to start at the back and work our way forward. Okay, as opposed to starting at the front, because I actually think they're easier at the beginning.
Yeah.
And then work our way back. Okay, so let's take a vote. Start at the back and work our way forward. Okay, start at the front and work our way the other way. Okay, work our way whatever. You know what I'm talking about. I'm still on cold medicine. Okay, well, we have more votes for starting at the back and working our way forward. Yeah? No, we don't ever. No. Yes, of course. So,
I put it was to be 12, but I was 8
okay, so if you have, one of the samples has n equals 4, so what's the degrees of freedom for that one? 3. And one of the samples has n equals 8, so what's the degrees of freedom for that one?
7.
And if you add 3 and 7 together, what do you get? 10. Okay? So the degrees of freedom was 10. Alright, so we're starting at the end. We're going down here to the end. Alright. Oh, that. Okay. A researcher wants to determine if an antioxidant supplement made from blueberries affects the cognitive functioning of elderly adults. A sample of n equals 16 adults between the ages of 65 and 75 is obtained. The researcher uses a standardized test to measure cognitive performance for each individual. The participants began a 2-month program in which they received daily doses of the blueberry supplement. At the end of the 2-month period, the researcher again measures cognitive performance for each participant. The results show an average increase in performance of 7.4 with a sum of squares of 240. Okay? So, what was the issue with this question? Where did you get stuck? Yes?
First off, I thought, that's why I asked the question in the beginning before class. It was a single t-test.
Okay.
Because I only saw like the end is 16, although they retested the.
Right, so there's one group of 16 adults, and they gathered data from them before they took the supplement, and data from them after they took the supplement. Right? So what does that sound like? That's a within subjects design. Okay? So it's one group of people, data was gathered from them twice, and then based on their scores, which I didn't give you because you don't need to have them, I told you that there was an increase in performance, so you know that the scores after were higher than the scores before, right? Because there's an increase in their performance. And the average of the difference scores, that's what M sub D means, right? It means the average of the difference scores was 7.4. Okay, the average of the difference scores was 7.4. Now, when we calculate a related groups t-test, how do we calculate t-observe? What do we do to calculate t-observe? Okay, right. So we're doing that one. It's t-observed for the related groups t-test. Whoa, it's really big. T-observed for the related groups t-test is the mean of the difference scores, right, over the estimated standard error of the difference scores, right? Okay, so I've just told you that the mean of the difference scores is 7.4, so that's the numerator, I just gave it to you. So now what you've got to figure out is estimated standard error of the difference. And all you've got to work with is the sum of squares of the difference scores. So how can you get from knowing that the sum of squares of the difference scores is 240 to a value for the estimated standard error? What steps do you need to go through? You need to know what the right degrees of freedom are, right? Because first you're going to need to get, right? You're going to need to get the sample variance of the difference scores, right? You're going to need that, and then that will take you to the estimated standard error of the difference scores. Okay? So the sample variance of the difference scores is sum of squares for the difference over degrees of freedom of the difference, and then estimated standard error of the difference scores is the square root of that over that, right? value, right here. So now you've got to get to here with information from the problem. So you know that this is 240. So now you've got to figure out the degrees of freedom of the difference. And how can you figure that out? So degrees of freedom of the difference is going to be, it's going to be the sample size for the different scores minus 1. And how many scores are you going to have in that sample of different scores? 16. Right? Because there's a different score for each person in the study. So that's going to be 16 minus 1, that's going to be 15. So now you know the degrees of freedom of the difference is 15. So divide 240 by 15 and what do you get?
16.
16. Look at that nice round number. It's almost like I planned the problem to be easier since you were doing it on your own. Okay, so now we know that the sample variance of the different scores is 16. So now we've got to calculate that estimated standard error of the different scores. So that's a square root now of 16 over 16. It's amazing. The square root of 1 is 1. So now I know that this up here is 1, which means that T observed is 7.4. Does that work? Yes, question.
Okay, so on the worksheet,
Yeah.
for the big S squared D equaling the sum of squares difference over the degrees of freedom difference, that's the same. That would be the same number for the.
So I'm not sure when you say the big S sum, so can I see which one you mean now?
So would this be the same calculation?
This should be this. No, this should be little s. It just made it look big on the sheet.
Oh.
That's just the estimated sample variance of the difference.
Okay.
Yeah. It just made it look like a bigger S, but it's supposed to be a little. There's only one. When you only got one S, it's a little S. Okay. Does that work? So everyone's okay with that one? So now we know that our T observed is positive 7.4. Now we're doing a two-tailed test with alpha 0.01. So what is our critical value?
2.95.
Okay. You said it's 2.95, our T critical. Does anybody have any questions about where 2.95 came from? Nope. Okay. So 2.95. And our observed value is 7.4, so we have a statistically significant difference. Okay. So do I retain or reject the null hypothesis? Reject. Okay, so reject the null hypothesis. And it says compute Cohen's d to measure the effect size of the treatment. Okay. So Cohen's d, the formula for Cohen's d for the related groups t-test is what? What's the formula? The mean of the difference over the sample standard deviation of the difference, right? Okay. So we already know what the mean of the difference is, right? 7.4, because we already got that in the problem. So now we've got to figure out how to get the sample standard deviation of the difference. And how do I get that? What's the secret? It's the square root of the sample variance. Okay. So that sample variance, it was a tough one, right? 16. So the square root of 16? Heck, you don't even need a calculator. So now we know that this is 4. So what is 7.4 divided by 4?
1.89.
1.89. There you go. So, small, medium, or large effect? Large. Remember, those tables for small, medium, and large aren't going to be on the test. You need to have them on your note card. Make sure you've got small, medium, and large for Cohen's d and small, medium, and large for r squared on your note card. Because if you come to me during the test and say, I don't remember what small, medium, and large, can you tell me? I'll say, I could. but I won't. You should know that. If you don't know, it should be on your card. That's why you get a card. Okay, so then it says, summarize the results of the study in one or more complete sentences, including an APA-style statistical statement at the end. And we're going to include what groups we're comparing, what we're comparing about the groups, whether or not there was a significant difference. If there was, the direction of the effect, and it's going to be clear from our description whether it was a between subjects comparison or a within subjects comparison. You want to go for it?
Yeah. Could you pull
Okay.
it up? Just so I remember.
Should I what?
Could you pull it up? I think it was the elderly.
Okay.
It's just that, okay, so is it elderly?
There's lots of different ways you could say this, so it's not that there's a fixed answer. I mean, there are answers that would be right and answers that would be wrong, but yeah.
Elderly adults who take a blueberry antioxidant supplement have higher cognitive functioning than if they did not take the supplement.
Okay, so that's close. I still am not clear that it's the same group of people.
Okay.
So I might want to put something in there like before and after.
Oh.
So elderly adults have significantly better cognitive functioning after taking a blueberry supplement for 2 months than they did before taking the supplement, or something like that. Does that make sense? Anybody else want to try another one? Yeah. Yes, absolutely.
Elderly adults between ages 65 and 75 who take a daily antioxidant supplement for 2 months perform significantly better on a standardized test of cognitive function than they did before taking the supplement.
Beautiful. That's the poster child of answers. that was, even Javier's nodding on, yeah, that's it, that's the answer. That's going to get you a big fat smiley face on the test. That's wonderful. Yes. Okay, so everybody got the idea how you would answer that? Anybody else have another one they want to run by me? Okay. So now the question is, what is the APA-style statistical statement? Here, let me switch over here. You guys talk me through it, and I'll write down what you say. What do I write first? Big T or little t?
Little t.
Little t, that's right. Little t, okay? Little t. Then what? Parentheses. 15, okay? Close parentheses. Equals. Positive. 7.4, okay? Comma. P. Less than. 0.01. Just kidding. Comma.
Two-tail.
Two-tail.
Comma.
Remember? Two-tail. Okay? Comma. D equals 1.85. All right, how many people got it? Yes! Victory over t-tests. Yep. Yes.
When we are answering a question about what our T-critical is for two-tailed tests, do you only want us to put like either positive or negative depending on what our T-observed is? You want us to do both?
Yep. So if I asked you, say at the beginning of this problem, I said, hey, up here, before you know anything, right? I say, what's the T-critical? And it's for a two-tailed test. You would say the T-critical is plus or minus 2.95 because you don't know yet, and you're doing a two-tailed test. So if it's a two-tailed test and you've got your critical value, you need to put plus or minus because you're showing me that it's a two-tailed test. When you actually do the evaluation, you know which one you're using, right? So when you know which one you're using, you only need to write the one that you're actually using. But ahead of time, you don't know which one it's going to be. So on the test, I will typically ask you to identify the T critical value somewhere, right? And if it's a two-tailed test, put plus or minus in front of it to show me that you know it's a two-tailed test. When you evaluate the null hypothesis, I'm not going to ask you to slot in things like this. I'm just going to say, okay, given the T critical that you identified and the T observed that you calculated, evaluate the null hypothesis, and then we'll say circle 1. Reject H sub O retain H sub O. Okay? So you're going to either reject the null hypothesis or retain. You're just going to circle which answer is the right answer given the finding that you have. Okay? All right. Yes.
When do we know when P is greater than or less than 0.01?
When do you know?
Yeah. Well, how do we know if P is greater or less than 0.01?
Well, you mean alpha?
Yeah. The alpha.
Okay, alpha and P are two different things, right?
Yeah.
P is the probability for getting a particular value. Alpha, so the default assumption on any assignment in here, including the test, is that alpha is 0.05. If I say something else, use the something else. Otherwise, you can assume that it's 0.05.
Okay.
So since I said 0.01, now how do you know that the probability of getting this value is less than 0.01? How do we know that? We know that because the probability of getting this is 0.01. Okay? That's what selecting that critical value means. This is what would get us at 0.01. And this is much further out in the tail, which means that the probability of getting it is much less than 0.01. And that's why in the APA style statistical statement we say the probability of getting, if I interpret this, what I'm saying here is, if we calculate a T observed of 7.4 with the degrees of freedom 15, the probability of getting that is less than 0.01 when we do a two-tailed test. And that indicates an effect size that is large at 1.85. So in order for us to get a statistically significant result, so if this is our critical value, our observed value has to be somewhere out here, right? And anything that's further out in the tail is going to have a lower probability than anything that's closer to the body. Make sense?
Yes.
Other questions? Yes?
To get the critical value, you use which DF did you use?
Which one would we use for this? We're doing a related groups t-test. What degrees of freedom would we use to look up the critical value?
The one that they did the thing
Degrees of freedom of the different
The degrees of freedom of the difference scores. So df sub d, which would be n sub d minus 1, right? So the degrees of freedom of the difference scores. So for related groups t-test, we use degrees of freedom of the difference scores. What do we use for independent samples?
Yeah.
df sub p, right? Degrees of freedom pooled, right? So it's either degrees of freedom of the difference scores, that's going to be big D as the subscript, or if it's lowercase p, that tells you independent samples, okay, alternate subjects. And I will put those clues on the test. I don't just put degrees of freedom nothing, okay? Because there's too many kinds of degrees of freedom we learn about in this class, and I want you to know which one we're talking about. So if you see degrees of freedom sub big D, then you know we're talking about a related groups test. If you see degrees of freedom sub lowercase p, you know we're talking about an independent groups test. Does that answer your question?
Not really.
Okay.
I mean, so the N, you just combine the two groups, DFs, or?
There are
Like-
two groups in this case. There's only one group.
Okay,
There's only
well then.
16. In this group, there's
Okay.
only 16 people. There's 16 adults, and we gather data from them twice.
Okay, I feel you.
So we gather data from them twice, and then we calculate a difference score for each person. So the difference between how they did before and how they did after, we get a score for them. And then when we take the average of those difference scores, that's going to give you 7.4. That's where that comes from. So when we do a related groups t-test, we're entirely focused on that sample of difference scores. And that's why we write the sample size lowercase n with, switch back over here. That's why we write the n with the sub d, because this is the sample size of the difference scores. That capital D is of the difference scores. That's what that stands for. So the degrees of freedom for the difference scores, the sample size for the difference scores, the sum of squares for the different scores, the sample variance for the different scores. It's all just those different scores. And that's why it looks like there's one sample, because you have calculated a different score for everybody. Any other questions? Okay. So which one do you want to do next? Now, are we doing it backwards because everybody did 1, 2, 3, and they didn't do 4, 5, and 6, and now they're just trying to see if I'll tell them the answers at the end? Whatever works. Okay. The stimulant Ritalin has been shown to increase attention span and improve academic performance in children with ADHD. To demonstrate the effectiveness of the drug, a researcher selects a sample of n equals 25 children diagnosed with the disorder and measures each child's attention span before and after taking the drug. The data shows an average attention span of a mean difference of 6.8 minutes with a standard deviation of 5.5 minutes. This is effectively almost exactly the same problem as the one we just did. It's just some of the numbers have changed. So you're going to do exactly the same steps. This is just, the only difference here is I've given you a different measure of variability than I gave you last time. So we start at the beginning, just like we did before. We know that T observed, right? The T observed we're shooting for is the mean square of the difference over the estimated standard error of the difference. And we already know what the mean difference is at 6.8. So now we're just trying to figure out what goes in that denominator. And last time we had sum of squares of the difference. This time we know the standard deviation of the difference. Okay. Now I've got to get from standard deviation of the difference to the estimated standard error of the difference. How am I going to do that? How do I get from standard deviation of the difference to estimated standard error of the difference? You can't just add n.
Divided by
the sample difference. So standard deviation on the numerator.
So what do you know about, I gave you 2 different formulas for calculating SMD, right? There's 2 of them. One is take the square root of that over that, right? That's one way you can do it. Another way you can do it is that. Now, you can get to either one of those, right? I mean, if you know you've got the standard deviation, how do you get the sample variance? What would you have to do? What's the relation? Just square it, right? If you do the standard deviation times the standard deviation, you get the sample variance. So you could do it that way if you want to. Or you can use the other form of the formula where the top has already had the square root taken out and you just do the square root of the sample size. Those are both totally legitimate formulas for calculating estimated standard error of the difference. And I don't care which one you use. As long as you show me the formula that you're using and you show me the math for the formula that you chose, even if there's a tiny difference, like because of rounding error or something between the 2 versions of the calculation, I will give you credit if you do it right for the formula you choose. So what would, if we know that, let's see, so I told you that, let's see, this is 5.5. Okay. So one way we could do this is 5.5 over the square root of, how many people are in this study? 25. So that would be 5.5 over the square root of 25, which is 5. So what's 5.5 divided by 5? 1.1. That's the easiest way to do it. Now what if we did it the other way? What if we did the square? What's 5.5 squared? Huh?
30.25.
Okay. All right. And then if I did 30.25 over 25, what do I get? What's 30.25 over 25?
1.21.
1.21?
We square root
And then what's the square root of 1.21? So whichever way makes sense to you, you can do it either way. It'll give you the same answer. Got it? Make sense? So you should be able to move among the different forms of variability. If I give you sum of squares, you should know how to get sample variance. If I give you standard deviation, you should know how to get sample variance. If I give you sample variance, you should be able to figure out what sum of squares is, right? You need to know the relationships among these things. That's 3510 stuff. So you want to make sure you understand the connection because you don't know which kind of thing you're going to get. All right. So if we know now that this is 1.1, what is my t observed? 6, positive or negative? Positive. 6.18. Is that what people got? Okay. And what is my t observed? Are we doing a one-tailed test, two-tailed? One-tailed test. Okay, so what's my t critical?
2.49.
I have a vote for what? 2.49. That's what we think it is, 2.49. Okay. Critical values by consensus. Okay. You did two-tailed? One-tailed. Okay. And we said 6.18. So, rejected null hypothesis, right? Cool. Rejected null hypothesis. All right. So, next question. R squared, right? We have to figure out the R squared. So how do we do R squared? What's the general formula for R squared? What's the general formula for R squared?
T squared divided by
T squared plus degrees of freedom. Right? What T are we using? Observed. And what degrees of freedom do we use for the related groups t-test? Difference, right? We always use the degrees of freedom that would be used to look up the critical value. So for related groups t-test, it's degrees of freedom of the difference. For independent groups t-test, it's degrees of freedom pooled. So our t squared, we said our t was 6.18 squared. Our degrees of freedom of the difference would be 24. Okay? So what does that give us? What's 6.18 squared?
38.19.
38.19. Okay. And what's that come out to? 62.19. Okay. So what do we get for our R squared? 0.61 or 61%. Small, medium, or large? Large. Super large. Really large. Very large. Godzilla large. That is a very, very big effect. All right. So somebody summarize the outcome of this study for me in words. Yes.
So with our squared, you never really want decimals with the percentages? Just
No, we report percentages as whole numbers. Because the percentage is already the decimal places. Because it's 0.61, that's already 2 decimal places. When we convert it, now it's already. So we report percentages as whole numbers. Otherwise, we're getting too precise, overly precise. So who's going to give me the outcome? Who's going to describe it to me in words? You have to say, switch back over here. Okay. Hold on one second. I know you know how to do it. I know Abby knows how to do it. I want to see somebody else do it. Because everybody's taking the test. Come Come on, brave souls. Come on, Remy. All right, Brandon, do you want to give it a shot?
Children with ADHD's attention span was significantly improved after the administration of Ritalin.
Okay.
Something like that.
Or something like that. Okay, I like that. So the attention span of children with ADHD was significantly improved after the administration of Ritalin compared to what? Before the administration. Right. Do you have another one? You had your hand up too. Want to read yours?
I said children diagnosed with ADHD who take Ritalin will show a significant increase in their attention span and improvement in academic performance compared to, and then, well, that's what I put, and then you would just have to end compared to when they did not take the Ritalin.
Mm-hmm. Sure, that would be good. Remember, we want to always talk about what we're comparing, so you want to be very clear that you're comparing them before and after they took Ritalin. So children with ADHD will show significant improvement in academic performance and in attention span after taking Ritalin than they did before. That works great. See, I knew other people had it in them. I believe in you. All right. So now we need our APA style statistical statement. Somebody give it to me. I will write it down so we can all check our work. Huh? T, little t. All right.
24.
Parentheses. 24. Okay. Equals. Okay. Uh-huh. Mm-hmm. Okay.
Oh, wait. 0.05.
Was it 0.01 or 0.05? 0.01. Okay. Comma. One tail. Okay. Comma. R squared. 61%. Yep. There you go. How many people got it? Okay. Yes.
So when you write that all together, so with the summary, which is in Word, and the actual APA style statement, what's the best way to like formulate that on the test? Because like I just wrote the statement and then comma that.
That's exactly what you're supposed to do. You're supposed to put the statement in words, and then you write comma, and you put that whole long thing, and then you put period at the end. And that's it. So if you wrote out, children diagnosed with ADHD have a significantly longer attention span and improved performance on tests after taking Ritalin than they did before, comma, that, golden. Fantastic. It's all one big thing. Okay, so we have now beaten related groups t-test to death. Let's make sure we've got independent groups t-tests. Okay? Gotta make sure we've got independent groups t-tests. So let's skip up here to an independent groups one. Do you view chocolate bar as delicious or fattening? Delicious, obviously. My daughter? Disgusting. Just care if it's fattening. She just thinks chocolate's gross. I don't know what planet she's from. I know she's my daughter. I was there when she arrived. But for some weird reason, she does not like chocolate. It says your attitude may depend on your sex. In a study of American college students, Rosenbauer and Cantonese examined the importance of food as a source of pleasure versus concerns about food associated with weight gain and health. The following results are similar to those obtained in the study. The scores are a measure of concern about the negative aspects of eating. So we know that there were 6 males in the study, 9 females. The average score for males was 31. The average score for females was 45, meaning that the women had more negative concern or more concerns about the negative aspects of eating than the males, at least in terms of their needs. Now what we're trying to figure out is, do they have a significantly greater concern about the negative aspects of eating than the males? And I gave you some of the squares. So now you've got to figure out if there's a significant difference between males and females. So, how do we do this? The formula for T observed for an independent groups test is what?
Sub 1 minus mean sub 2.
Okay. Over.
X
Mm-hmm.
sub mean 1 minus mean 2.
Yep. Okay, so it's the difference of the sample means, right, over the estimated standard error for the pooled samples. Yep. Okay. So, what do we know already about these two? We can pick whichever one, because one is males and one is females. We don't know one or two. Which one do you want to put as one and which one do you want to put as two? Because they're just males and females. There's no one and two. So what do you want to do?
45 minus
You want to do, we're going to treat the females as group 1 and the males as group 2. It doesn't make any difference. Right? Okay. But it's easier to do the math that way, then all the numbers come out positive. That's always nice. It's nice when the numbers are positive. It's easier to work with the negative numbers. Okay. Yeah.
So you can switch it around.
Yeah, because right now, because the prediction is it's a two-tailed test, right? So you're not saying that any one group is supposed to be bigger than the other group. Who's the experimental group with males and females? I think each group would say the other, right? I'm the control and you're the experimental group, so make it so that the math works and makes sense. If it comes out that the female score is clearly higher, so yeah, it doesn't matter. All right, so we do 45 minus 31 on the top. What does that come out to? 45 minus 31? 14. Okay, now we have to figure out this thing on the bottom. So how do we get to there from what we know? We know sum of squares. Sum of squares for the females is 680. We know the sum of squares for the males is 490. Okay? Oh, the enthusiasm. You're like, oh gosh. Here we go. All right. So how do I get from there to that pooled estimated standard error? What do I do next? We have to find variance. We need pooled sample variance, right? I need to get to here somehow, right? What's the formula for pooled sample variance? Sum of squares pooled over degrees of freedom pooled. How do I get sum of squares pooled?
Sum of squares 1 plus
Sum of squares 1 plus sum of squares 2. How do I get degrees of freedom pooled? Degrees of freedom 1 plus degrees of freedom 2. Okay, living on the wild side now. 680 plus 490 over, what's my degrees of freedom and how do I know? What's my degrees of freedom for group 1, females? 8. Right, my degrees of freedom for group 1 is 8. What's my degrees of freedom for group 2, males? 5. Okay, so what's 680 plus 490? 1170. Okay, and what's 8 plus 5? All right. So if I do that math, what do I get? 90. 90. Oh, those nice round numbers. Okay, so now I know that my pooled sample variance is 90. So now I need to get my estimated standard error, and that's the big scary formula, right? Right? Not S2P plus S2P over N sub 1 plus N sub 2. Don't do that. Okay, so square root of 90 over, and so my sample size for females is 9, and my sample size for males is 6. Okay? The square root of, that's going to be 10 plus, what's 90 over 6?
15.
15. Oh my gosh, it's crazy. Square root of 25. 5. Okay? So now I've got the value up here. This is going to be 5. 14 divided by 5. 2.8. I have a vote for 2.8. Yeah? We're not sure?
2.8,
That's right?
yes.
Okay. Okay. So we've got 2.8. Now what? I'm trying to figure out if there is a significant difference between males and females. We put the females first because they had the larger score. So what we're saying now is that the T observed that goes with that is 2.8. What's the critical value? We're doing a two-tailed test, and alpha is 0.05. So what was our critical value? What did you say it was? 2.16?
Yes.
2.16? Now, if you did it the other way, if you did the math the other way, right, you would have gotten a negative number up there, and you'd be using the negative critical value, right? So if you did it so that the number came out positive, you're going to do it like this. And you get a significant result. Remember that we're talking about, in this case, we're talking about that tail, right? If you did it the other way, so it was negative, that's also right, because it's a two-tailed test. You can do it either way, it makes no difference. Okay? Then, what you're doing is you're looking at the negative tail. So the critical value is here, and the observed value is out here. So you put these in the opposite order. This is negative 2.16. This is negative 2.8. Right? And that number is still bigger. And either way, those are going the direction to tell you to reject the null hypothesis. Okay? Make sense?
Yes.
All right. So, we're rejecting the null hypothesis, so there is a significant difference. Which test did I ask you to do? R squared. All right, so now we're doing R squared for independent groups t-test. We said before it was t squared over t squared plus degrees of freedom. Which degrees of freedom this time? Not degrees of freedom of the difference. We don't have any difference scores. What degrees of freedom do I use? Pooled. Okay, so we had 2.8 squared over 2.8 squared plus, what's our degrees of freedom pooled? 13. What's 2.8 squared? 7.84. What's the numerator come out to be? 20.84. Okay? And what's 7.84 divided by 20.84? 0.38 or 38%. Okay, small, medium, or large? Large. All right. So, second verse, same as the first. Summarize the results for me in sentences and then an APA-style statistical statement. Let's go back and see what we're looking at. Following results. Okay, so we're comparing males and females, and we're measuring their concern about the negative aspects of eating. Where the females had the higher average and the males had the lower average. And we found that that difference was statistically significant. So how do I say that? In a sentence or two. Come on, brave souls. Now's the time to find out if you can do it, not on the test. I'm going to pick somebody. I like all the people who are trying to avoid making eye contact right now. That's pretty awesome. I see you hiding over there. You're trying to hide in your scarf. I see you. All right, go ahead, give it a try. Yeah, you can do it. So what groups are we comparing?
Women and men.
Oh, women and men, yeah, we're comparing males and females. Okay, good. So we're comparing males and females. And what do we know about them? Uh-huh is not an answer to that question. What do we know about them? That. Good.
They were measuring the negative aspects of eating.
That's right. We're measuring their concern about the negative aspects of eating. And what do we know about men and women and their relative concern regarding the negative aspects of eating?
That.
Yes.
The observed was higher.
That's true. So who has more concern about the negative aspects of eating?
Women.
Women. Okay? So females, was it a significant concern? Significantly more concern?
Yeah.
Oh, so how would you say that?
Okay. After. Okay, hold on.
It's not after. There's no before and after this time. It's all at the same time.
When the importance of concerns of negative aspects of eating was measured, women were more concerned about chocolate being fat.
Well, we're not specifically measuring
than men.
Okay. That is progress. I like that. Okay, so a lot of the stuff in there was totally right. Actually, we're not actually measuring for sure about chocolate, although you could say that if you wanted to. We're comparing men and women, or males and females. We're measuring their concern about the negative aspects of eating. We know that females have more concern. We know that they have significantly more concern. So we can say females showed significantly more concern about the negative aspects of eating compared to males. Done. That's it. You can do that, right?
Yes.
Yes, you can. Okay. So males, so just make sure when you see a table like this, right? I'm telling you what groups we're comparing and what terms you should use. So it's not a trick. No tricks. So females show significantly greater concern about the negative aspects of eating compared to males. Okay? Now, walk me through that APA-style statistical statement. Small t, parentheses, 13, okay, equals, positive 2.8 or negative 2.8 if you did it the other way. Either one is fine as long as you use your observed value,
I
okay?
have a question.
Yeah.
Could, since it's a two-tail test, and I know on the other problem test it was two-tail, and if we didn't test it out yet, we would put plus or minus. Could we do plus or minus there, or would we have to write them both separately depending on how we?
This is an
calculate?
observed value. It's only one.
Okay.
So it would always be either positive or negative, never both.
Okay.
Observed values are never both.
Okay.
Only a critical value can be both. Okay? So, positive 2.8, comma, what? P less than 0.05,
Two, comma,
comma,
two chain,
two-tailed,
comma,
comma,
R
R squared
equals
equals
38%.
38%. Okay, good. All right. Are there any specific questions that you guys have? I mean, we can sit here and walk through the problems, but are there specific questions that you guys have, places where you got stuck, that I can help you get unstuck? Brant, you said earlier you thought that there was a trick question in here. Is it untrickified?
It's untrickified.
All right.
F max.
F max. No tricks. Yeah.
Oh, yeah, that was mine.
What about it?
Number 5.
Number 5. Explain why a researcher would perform an F-max test prior to performing a t-test on 2 independent samples. Okay? What's challenging about that question?
It's only for variance, sources of variance only.
It's for what?
Sources of variance only.
Well, we're interested in evaluating sources of variance, but what's the main difference between well, what's F-max for? What do we use it for?
Homogeneity of variance.
Homogeneity of variance, right? Where did you learn that information if you weren't in class? Where is that information contained?
The handout.
The handout. There's a handout, right? And in the handout it says, there's this thing called homogeneity of variance, right? And what's homogeneity of, what does that mean? Homogeneity of variance. Similar variances, right? It means that they're similar enough what? To compare, that's right. You know that, I'm all about that. Biggest issue with an independent groups test between subjects comparison, right, is are the groups similar enough to compare to start off with, right? If they're too different in the beginning, then you're going to get a type 1 error. You're automatically going to get a significant difference between them, and that's not any good. You need your manipulation to be the cause of the difference, not the fact that they were already so different to start off with. So F-max is for assessing homogeneity of variance. It's a way for us to statistically determine whether or not the groups are similar enough to proceed with the analysis. Okay. So why do we do an F-max test on independent samples but not related samples?
Because related samples are already
It's already the same people, right? In a related samples t-test, you're comparing a group of subjects to themselves. So you already have homogeneity of variance. They're already similar. They're similar to themselves. And granted, you're not the same person today that you were yesterday. You've grown some, maybe. Maybe you've gained weight, maybe you've lost weight, maybe you're happier, maybe you're sadder. Maybe you're richer, maybe you're poorer, maybe you're smarter. Maybe you've killed some brain cells between now and then, I don't know. But, in general terms, you're about as much like you as anybody could possibly be. Right? You're about as close to yourself as anyone could be. So, if I compare your performance on one measure yesterday and your performance on another measure today, I really don't have to worry that it's going to be that much difference. So when we have an independent samples test, we have to do it to determine whether or not the groups are statistically similar enough to move on with the analysis because of individual differences in the two groups. We're worried about that. But in a related samples t-test, I don't have to worry about it because it's basically the same subjects just getting tested again. So I can be confident homogeneity of variance already exists. Yes?
So can I read my answer to see if
Absolutely. I encourage you to do so.
Okay, a researcher performs an Fmax test prior to performing the t-test on 2 independent samples in order to see whether or not both groups are similar enough to compare to one another. The Fmax test is unnecessary for related groups because these groups have been proven to be homogeneous, thus they are similar enough to compare.
Okay? The only concern I would have with that answer is that the second part doesn't make it clear that you're comparing one group to themselves.
So mention the related group.
So when we talk about, the first part about the independent samples was fantastic. The second part, when you're talking about related samples, you're really talking about the same group of subjects being tested under multiple conditions. And so it's the same group of subjects, so individual differences are no longer a concern. That's the only distinction I would want to make. But other than that, fantastic. Well done.
So can you put for the second part that they're the same, because they're the same sample size?
It's not the same sample size, it's that it's the same subjects.
Okay.
When we do a related samples test, we're comparing a group of subjects to themselves when we've tested them at 2 different points in time. And we just don't think, even when we test them, 2 months apart or a year apart, there's nobody who's going to be more like you than you. So we've got homogeneity of variance. If I'm comparing you to yourself, we're good. Because you have the same educational background, everything about you is pretty much the same except whatever I've done to you in the experiment. So if I get a difference, that's good. That's what I was looking for. Any other questions? Yes?
Well, could you do the Fmax test for the data in number 3?
Sure. I'd be glad to. Okay. So in number 3, it says we should do an Fmax test. In order to do Fmax, okay, Fmax observed is the larger sample variance, or the largest sample variance for all the samples you're looking at, divided by the smallest sample variance for all the samples you're looking at. Now right now we're only looking at 2 samples, so it's going to be the larger one or the smaller one. So how do I figure that out? Well, I'm going to have to calculate the sample variance for group 1 and the sample variance for group 2. The sample variance for group 1 is going to be the sum of squares for group 1 over the degrees of freedom for group 1. Now we decided that, so if we look at number 3, again we've got type A and type B. So in this case, A1, B2. Is that okay? A1, B2, okay. So the sample size the sum of squares for group 1, type A, is 740. And the degrees of freedom for group 1, or the type A group, is 8 minus 1, so that's 7. So what's 740 divided by 7?
105.71.
Huh?
105.71.
105.71, okay. So this is for type A. And then for the second group, it's going to be 660 divided by what? Also by 7, because the groups are the same size. So what's 660 divided by 7? 94.29. So for type B, it's 94.29. So now I'm going to do the formula up here. And I'm going to put the larger one of those numbers on the top and the smaller one on the bottom. And what do I get when I do that math? 1.12. Okay, so that's my observed value. Now I've got to figure out whether or not that's significant. So I have to go look up Fmax critical. And F-max critical, you look that up in your table, right? You have your packet with you. You're going to get a packet just like this for the test. Okay, but you don't get to use your own packet. I'll give you one. All right, so we're going to look up critical values for the F-max statistic. What kind of stuff do I need to know? I need to know n-1, I need to know the number of samples, and I need to know what my alpha is. Okay, so I'm doing a t-test. We always consider t-test to have 2 samples in this class, right? Even if it's within subjects and it's before and after, each one of those is effectively a sample, right? That's why we call them related samples, because they're using the same subjects. Okay? So we've always got 2. So for t-test, we're always looking in the 2 column here. Okay. Now, what's our alpha for this problem? 0.05 or 0.01? 0.05. Okay, so that means we're looking in light-phase type. These are the numbers on the top. And now it says n-1. What n are we talking about there? Nope. N common, right? They have to have the same n, otherwise you can't do F-max. So the common n, the n that these 2 samples share, is 8. So 8 minus 1 is 7. So we go here to 7. And we go look and see what the 0.05 value is, and it's 4.99. So now we come down here, put the critical value here, observed value here. Critical value is 4.99, observed value is 1.12. So what's the relationship between these 2 things? Okay. So do I retain or reject the null hypothesis? Retain. Is that good or bad? That's good. Because what does it mean when I retain the null hypothesis? It means there's no difference between the groups. And what groups am I comparing here? I'm comparing their variances, right? And what I'm finding is that the variances are not different from one another. Well, if the variances are not different, that means they are the same, which means I have homogeneity of variance, and I'm good. I like that. That means I can proceed with my analysis because the samples are coming from the same population. Okay. Good? Make sense? Does that help? Saw that all the way through? Okay? Yes?
Is that where you would stop at that problem? Because I did all that and then I got confused. I don't know why. It's because at the end it said then use a 1-tailed test, but all that's already included, right? Or do we continue on?
So that you do this first,
Okay.
right? So technically you calculate F-max first because that tells you whether the groups are similar enough to compare. Since you've retained the null hypothesis here, that's good. Now you can go ahead and do the rest of the t-test.
Okay.
And now you can actually trust that the results don't represent some kind of weird type 1 error because the groups were already super different. Okay? So the test. It's going to be just like this. You're going to get problems. I'm going to ask you questions just like I asked you here. It's going to be laid out just like we did in the practice, where I say, calculate this, now calculate this, now calculate this, now calculate this, now calculate this. You need to have all your formulas, all of your tables for effect size stuff on your note card. All you're going to have is your test packet that you're going to write all your answers on, do all your math on, and a copy of this packet of critical values. You may have seen, I may use problems from the problem set, 1 or more, but I may also give you original problems. You could probably bet on 1 problem coming from the problem set and 1 problem being totally original. You've never seen it before. But you should be able to answer questions about F-max, in essay form without a problem. You should be able to answer questions about the article that are relevant to what we've been talking about. So, like I said before, what was the independent variable? Was it a between groups variable or within subjects variable? If I show you the table from the paper, you should be able to read the table, tell me what was significant or wasn't significant. Basic stuff like that. Did they do one-tailed test or two-tailed test? How do you know? Things like that. Does anybody have any other questions about the test? Or about the problem set? So there are extra practice problems, right, that are available online. The TAs have copies of the key. The TA lab also has a copy of the key. So if you're doing review in lab for the test, you can work on those problems and the TA knows the answer. So you can get help in lab too. And I recommend that you spend time in lab cranking on those problems. Practice, 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 practice. Because I might pull the problems off the extra practice, not the problem set. So it's worth doing every problem I give you. Be familiar. All right, go forth and be awesome. See you on Monday.